Yeah. So with that in mind, today we're going to use conservation of momentum to do some example problems, and those example problems um, will um, be primarily about collisions, right? So collisions, or I like this new word that I got from that video, is explosions, right? Because I always use collisions generally, whether it was two things running into each other and either bouncing off or sticking together, or two things that started out together and then pushed apart, right? So we could call that an explosion. But in either case, momentum is always going to be conserved, and then in certain situations, kinetic energy will also be conserved. Let's first do an example of an elastic collision. So in an elastic collision, the thing that you should remember is that kinetic energy is conserved also. Okay, so momentum is always conserved as long as there's no forces from outside the system that's been defined. But only in certain cases you have to be told that the collision is elastic in order to say that kinetic energy is conserved. Oh, and just, so you should be able to, if you have a question, please unmute yourself, or it worked pretty well for people to ask questions or make comments in the chat. That'll pop up as well. Although I am kind of looking down and back up, so it might take me a second to see that somebody's asked a question in the chat. But please definitely interrupt, stop me if anything's unclear. Okay, so in this example, elastic collision, we'll just take a simple picture where we have some mass that I'll call m1 that has some initial velocity, and it's going to collide with another mass which is initially at rest, and this mass I'll call m2. Right, so we'll have some V1 initial, but V2 initial is going to be equal to 0. And as usual, we want to pick a direction that we're considering to be positive. So I'll say to the right is positive, like we usually do. Okay, so the initial velocity of block 1 is positive. So we know that the overall momentum is positive. So in the end, we should get a positive momentum. Now, we're keeping this a little bit general. I do want to specify here a particular mass for M2. Let's just say that it's twice as massive as M1. Right, so what happens if you have an object in motion and it runs into something that's twice as massive, that's at rest, and they collide elastically? Okay, so did I just, oh, okay. So we do as I said in the video, in general, if we wanted to get like a general expression or figure out what happens here, the algebra can get a little hairy, but for a particular situation like this, we can deal with it. Okay, so the first thing that we want to do is write down the initial momentum, right? The total initial momentum for the system. So I'll write that as P sub I, and that's a vector, although this is in one dimension, so we only have to worry about positive versus negative. So momentum initial is going to be equal to, if we have two objects, it's m1 times v1 initial, and then it's plus m2 times v2 initial. But in this case, we've said that the initial velocity for object 2 is 0, so that term will go away. Right, so we just have m1 v1I. And then our final momentum, P final, is going to be m1 times v1 final plus m2 times v2 final. So conservation of momentum tells us that the total initial momentum is equal to the total final momentum. So we can just set those two equal to each other. So we've got m1 v1 I. Sorry, that try and make my I's look different than my ones. v1 I. And then that is going to be equal to m1 v1 F final plus m2 v2 final. Right, so if we look at this equation, we know the masses, and we're trying to find everything in terms of the initial velocity. So what our unknowns are is really just v1 final and v2 final, but that's two unknowns. So we know that always with momentum, because there's going to be two unknowns, right, the final velocities of the two objects, we always need additional information. So if it's an elastic collision, that additional information comes from the kinetic energy conservation. If it's inelastic, then we need to be told something else additional. But we'll do an example with that after this one. Okay, and then the last thing that I can do to make this a little bit simpler is to remember. So we can remember that M2 is twice M1. So we can use that information down here. So let me write that again. M1 v1I is equal to m1 v1f plus 2 m1 v2f. And so if we look at that, then we can say, well, there are there's a factor of m1 in every term. So if I divide both sides by m1, that's going to cancel out. So I'll go ahead and cancel that out all the way through. Now you can only do that if a term appears in, if a factor appears in every term on both sides, but it does in this case. Right, so that's going to make our equation look much easier to deal with. So we've got v1I is equal to v1f plus 2 v2f. All right, so that's one equation that we have. So that's the equation that we can get from conservation of momentum. Now, because it's an elastic collision, we will also have kinetic energy conserved. So we can just write that out. In general, that's going to be 1/2 m1 v1I squared plus 1/2 m2 v2I squared is equal to 1/2 m1 v1f squared plus 1/2 m2 v2f squared. Okay, so the first thing that you could say, well, the 1/2 is really redundant. It's in every term. I don't want to have to copy that down. Right, so I'll go ahead and cross it out. So I left it in there just because that is, there's a 1/2 in kinetic energy expression. So I wanted to include that just so that we don't forget that when we do other kinetic energy problems or calculate the kinetic energy directly, we need to include that factor of 1/2. Okay, the other thing I can do is I can say that V2 initial is 0, right? So this whole term goes away. And finally, this M2 is equal to 2M1. So when I do that, well, let me go ahead and write it. I'll have M1 V1I squared is equal to M1 V1F squared plus 2M1, right? Because I just replaced what M2 is, times V2F squared. And again, that means that this mass cancels out, right? So this is going to be generally true for any situation where, a mass is colliding into something that's twice as massive. All right, so that gives me, might as well copy it down to have a clean expression to draw a box around. I've got V1I squared is equal to V1F squared plus 2V2F squared. So now I've got two equations with two unknown final velocities. So by the fundamental theorem of algebra, that means that I can solve. Okay, so now the issue here is because I have two unknowns and two different equations, even if I had numbers, even if I said, well, let's make the initial velocity 3 meters per second or something like that, I couldn't calculate, I can't just solve either one of these equations on its own, right? I have to combine them together somehow. So the way that we do this is, okay, I say, I need to solve one of these equations for one of the unknowns and then plug that into the other equation. Now, if you look at these two, which one do you want to deal with first? The thing you'd want to deal with first would be the simpler equation, right? So the one without the squares in it. So when we do that, let's go ahead and so I want to solve this. It doesn't matter which one I'm going to solve it for, but I'll solve it for V1F. Right, so I will subtract V2F from both sides, so I get V1I minus 2 V2F is equal to V1 final. So now I can take that expression for V1 final and plug it in right there. Okay, so let's go ahead and do that. So when I do so, I'll have V1 initial squared is equal to, let me keep that on screen. There we go. So I've got V1 initial squared is equal to, okay, so it's V1 final quantity squared. So V1 final, I solved from the other equation as V1I minus 2 V2F, and that's quantity squared. And then I still have the next term in this equation, which is 2 V2F squared. Okay, so as complicated as it might look, this is an equation where the only thing that I am considering as an unknown is V2 final. So that means I can solve this. Okay, so the first thing that I have to do is square out that term in parentheses. So you have to remember whatever method you learned in algebra to multiply out a polynomial. So it's this term times itself, right? So you can use the FOIL method. So when you do that, you're going to get the first term squared. So I'm going to have V1I squared. Then I'm going to get also the second term squared. So that's plus 4 V2F squared. And then I'm going to get 2 times the first term times the second term. So that's going to give me minus 4 V1I V2F. And then I've still got this final term there, so I need to write that down. So I've got plus 2V2F squared. Okay, so looks nasty, looks quadratic, but it's actually not going to be because some things simplify. So one thing that I'll notice is that I've got V1I squared on both sides. So if I subtract that term from both sides, these are going to knock each other out of the equation. So that's nice. That simplifies things a little bit. So let me go ahead and recopy what that equation looks like now. Let me see if I saw that. Saves a little writing time. So I just copy those terms down. On this side now I've got 0 is equal to that, and I can erase that plus sign just to make things a little clearer. All right, so now if I look at this expression, this still looks quadratic. Okay, first of all, I've got 4v2f squared and 2v2f squared, so those are good. That's the same term. I can combine that into 6 v2f squared. So let me do that. So just combining those two terms into one with the prefactor. So let me erase and then write the 6 there. Okay, now step back again. And what I see is there's a v2f in each term on this, and the other side is 0. So if I just divide both sides by v2f, then I can partially cancel that out. So that squared, one factor of it goes away in the first term, and then there's only one factor in the second term. So that finally gives me 0 is equal to 6 v2f minus 4 v1i. Okay, so I'm trying to solve for v2f, so get those things on opposite sides. I'll have 4 v1i is equal to 6 v2 final, and then divide both sides by 6. So that's going to give me v2 final is equal to 2/3 v1i. So what does that mean? That means that the object that was originally stationary is going to go to the right with a velocity 2/3 of what the initial velocity was. So, if it comes in with a velocity, if the first object hits it while moving at 3 meters per second, the originally stationary block will move to the right at 2 meters per second. Now that was a long way to go, but that's not everything, right? We also want to know what v1 final is. So if I go back up, I solve this equation here. So I've got that solved for v1 final. So I know that v1 final is equal to v1 initial minus 2 v2f, but I just solved for v2f, and that was 2/3 v1i. And so that gives me, I'm going to have v1i minus 4/3 v1i, which means that v1 final is going to be equal to negative 1/3 v1 initial. So that means that the original object that came in and crashed into the larger object, it's going to bounce backwards, right? But not as fast as it was initially going, right? So just to put some numbers on this, right? If v1, I don't know why I wrote 1/f. That was supposed to be a word, if. Getting too much in the math mode. If v1 initial, just to make an easy value, 3 meters per second, then that means afterwards, after the collision, I'm going to have m1 moving to the left at 1 meter per second, and m2 moving to the right at 2 meters per second. Right, so now we don't need to spend the time to check here, but a good check is always just to go back and take those final velocities and plug them into both the momentum and kinetic energy equations and make sure that those quantities actually ended up being conserved. That you have the same number before the collision as you do after the collision. Okay, so like I said, that was the elastic collisions, because we're dealing with two equations and two unknowns, and there's things that are squared. Though that algebra gets a little bit messy even in this. We weren't trying to solve it in general. We were just trying to do a specific example that was actually kind of simplified. Right, one of the objects was at rest initially. If we had made it not at rest initially, the algebra would be even more involved. So we are going to look at a peregrine falcon. So a peregrine falcon. This is a video from that was attached to a falcon. So these are the fastest moving animals in the world. So they move at their fastest when they go into a dive. All right, so that's our bird's eye view of what's going on. We can also see this guy researches peregrine falcon dives by skydiving next to them. Let me find them. All right, so we can see the extreme aerodynamic position that the falcon goes into in a dive, or as it's called in falconry, a stoop. All right, so we can see the extreme aerodynamics there. Can get up to 200 miles an hour. And why do they do that? They do that so as part of their hunting. So let's go here. So here is a video of a different falcon, the one with the back cam, taking a duck. From midair. So this is going to be our example of a perfectly inelastic collision. So perfectly inelastic is so objects stick together. So if you are a falcon, you want to catch the duck after you collide with it, so that you can eat it. So in this picture, let's start with this. So we're going to take, because everything's moving downward the whole time in this picture, I'll go ahead and take down as a positive direction. And then we've got our falcon. We'll see my best falcon picture. There we go. Wow. The falcon is moving initially downward. So the mass of a peregrine falcon, a male peregrine falcon, which is actually smaller than the female, is 0.7 kilograms. And the initial velocity that we'll take here is 90 meters per second. So about 200 miles per hour. So the top speed in a dive. And then we've got, a figurative sitting duck, but I guess a literal flying duck. Wow, okay. That's supposed to be a wing. There's some feet. Okay. And so the duck is probably flying at a low velocity horizontally, but just to make things easier, we can say that the velocity is basically 0 for that duck. And the mass of the duck, I use a typical mallard duck of about 1.2 kilograms. So the question that I would ask here, well, first of all, after the collision, how fast is the peregrine falcon moving? You could see in that video, the duck was pretty close to the water. So the falcon's going to have to stop really quickly after hitting the duck. And then also we could say how much energy is lost in the collision, because that will let us know how much energy the falcon is putting. The kinetic energy is lost. That means that's going into energy of injuring and killing the duck. Okay, so in an inelastic collision, all we have is momentum. Momentum is always conserved in collisions. So we've got initial momentum. Wow. Okay. I'll try again. The letter P, I forgot how to write it at some point in print. And my cursive P's really bad looking. Okay, so we've got our initial velocity is going to be the mass of the falcon times its velocity, which I labeled as VI, and then plus the mass of the duck times its initial velocity, but that was just 0, so that term goes away. And then the final momentum, P final, is equal to the mass of the falcon times V final, and I know I'm using F as a double duty subscript here for falcon and for final, plus the mass of the duck times V final. Now, there's two ways that you can think about this. You could say, I've got two objects that both have the same final velocity, or you could kind of treat it as a single object, right? It's a, if we were looking at this, we would just see a mass of feathers, right? So you would see an object that has the combined masses, mass of falcon plus mass of duck times, and they're both together moving at the final velocity. So algebraically, that's the same, right? Basically, I just factored out a common term, but it might be easier to say, well, I have to sort of mentally picture, I have a single object, right? It's two things that are stuck together moving at whatever this final velocity is going to be. So setting those equal, right? Conservation of momentum, I've got the mass of the falcon times V initial is equal to mass of falcon plus mass of duck times V final. And I know everything except the final velocity, so let me use my paintbrush here. So I'm going to divide both sides by that combined mass, so that's mf plus md. Right, I'll divide this side by mf plus md. And so that gives me that V final is equal to m sub f over m sub f plus md, and that's all times V initial. So using our given values, I've got 0.7 kilograms divided by 0.7 plus 1.2, that's 1.9 kilograms, and then times 90 meters per second. And that gives me a final velocity of 33.2 meters per second. Now, I really should just keep two sig figs here, but I'm keeping an extra one because our secondary question was how much energy is released, or how much kinetic energy is lost in the collision. Said it's not really doesn't like vanish into nothingness. It's going to go into the internal energy of the duck, which is what breaks its bones and kills it, so that the falcon can eat it. So the change in kinetic energy is just the final kinetic energy minus the initial kinetic energy. So that's going to be So I've got 1/2. So the final kinetic energy is 1/2 of the combined masses. So m falcon plus m duck times the final velocity squared. And then I'm going to subtract 1/2 of the mass of the falcon times the initial velocity squared. Right, because in the beginning only the falcon was moving, so I don't have any kinetic energy from the duck. All right, so plugging in the values that we just calculated for the final velocity, we get that this is a change of negative 1,790 joules. Now I look at that number, I don't really have a lot of context for, you know, what's 1,790 joules worth of kinetic energy that was transferred during the collision. So I like to compare it to something that I can kind of visualize how much energy is that. So I could compare it to a gravitational potential energy. Right, so this gravitational potential energy, if this would be like if I were dropping a rock on something, right? So if this is what I calculated was, this would be like dropping a 40-pound rock from 6 feet. So, you know, just because I'm comparing it doesn't mean I'm advocating doing this, but, you know, you wouldn't want to drop a 40-pound rock from over your head onto your foot, and certainly wouldn't want to do it on a duck, right? Unless you were a falcon trying to eat it. So, you know, this is the reason why the falcons do such extreme dives, because, well, for one thing, it allows them to sneak up on the duck, right? The duck's never going to see the falcon coming until it's too late. But then also there's going to be a large amount of energy, kinetic energy, that becomes then energy within the duck in the collision, which good for the predator, bad for the prey. Now I'm going to share a video of an example that I did in my backyard for the Sycamore Physics Instagram page. So here I have a basketball and a tennis ball. It's actually a squeaky dog toy, but works about the same. And so I'm going to drop one over the other. And so this is actually kind of good to do outside because, as you'll see, I wouldn't be able to do this in the classroom. So the basketball and the tennis ball aren't that bouncy on their own. So you can see the tennis ball shoots up out of the frame and you know, bounces a lot higher than you might expect. Okay, so this is, you know, in reality, it's not going to be a truly elastic collision, but, you know, for a physics problem, we can treat bouncy balls as if they're fairly elastic. So I'm going to do an example of a slightly different situation, just because it makes the calculations a bit easier. So in this case, we're going to have our bouncy balls. Okay, so let's do the stacked ball. This is a classic demo. So, okay, I'll take up to be positive for this picture. And I'm going to, for this example, I'm going to have a ball with mass m, and I'll have the lower ball be 3 times as massive. All right, so that's not the right ratio for a tennis ball and a basketball, but it makes for a good example, as we'll see. So what happens in this, I need to talk with my hands, so I'm going to start my video. So what happens in this demo is that because you drop the 2 balls from basically the same height, by conservation of energy, when they reach the ground, they're moving at the same speed, right? But the lower ball hits the ground and bounces back up. So if it's elastic, when the lower ball hits the ground and bounces back up, because it's bouncing off the earth, which is huge, right? It's basically going to bounce back up with the same velocity that it had when it hit. So that means that we have a ball that's moving up at a certain velocity and a ball that's moving down at the same speed but opposite directions. All right, so done talking with my hands. So I've got a ball moving down at a certain velocity and a ball moving up at that same velocity but opposite directions. Okay, so now that's before the collision. So I'm going to say after the collision. Now, if this is an elastic collision, we should be able to solve this, but it's going to be messy algebra. So what I'm going to say is after, if you pick these particular masses, we're going to have this ball and then the bottom ball. We find that this one has a final velocity of 0. So then we want to know the final velocity of this ball equals question mark. We want to know what velocity, final velocity it would have, and then we can check, is this elastic? Okay, so first let's do the momentum. So P initial is going to be equal to, so remember we've got up being our positive direction, so the bigger ball has positive velocity of 3m is its mass, and then times, I just called it v, and then minus the upper ball has a momentum that's negative because it's moving down. All right, so I've got 3mv minus mv. Well, I can just simplify that. That's 2mv. So now P final, we've got the mass of the little ball times V final plus, just for completeness, I'll write the momentum of the other ball, but that has a velocity of 0, so this term is clearly 0. So this expression becomes mass times V final. So that means I've got, by conservation of momentum, I've got 2mv, that was the initial velocity, is equal to m v final. Again, I see that there's a mass in both sides, so that tells me that v final is just going to be equal to 2 times the initial velocity. So the tennis ball bounces up off of the basketball with twice the velocity that it would have if it had just bounced on the ground. So that's why the tennis ball goes so surprisingly high, because this means that if you double the velocity, you're going to quadruple the kinetic energy, and therefore by the time it gets to its maximum height, it's going to get to 4 times the drop height. So in that, where I dropped it from about 6 feet, in a perfectly elastic collision where the ball or where the mass ratio was 3, we would expect it to get to 24 feet in the air. Now it doesn't quite get there because, as I said, these balls are not truly elastic, and especially the tennis ball being a dog ball, a squeaky dog toy, not super bouncy, but bouncy enough for the demo. Okay, so the last thing that I wanted to do was check, because here, like I said, you need to be given additional information. And so what I did was I told you the final velocity of one of the objects. That allows me to solve for the other final velocity. So I would find my kinetic energy initial, which is 1/2 m. So this is for the small ball, so that's 1/2 mv squared. And then for the larger ball, that's going to be 1/2 times 3m times v squared. So that gives me 1/2 plus 3/2 is 2/2, which is 2 mv squared. And KE final, again, only the small ball has kinetic energy, so that's 1/2 mv final squared. But I found that v final was 2 times the initial velocity. So 2 squared is 4 times 1/2 is 2, so that gives me 2 mv squared. So these two things are the same, which makes me happy. So that means that the kinetic energy was conserved, and it is an elastic collision. Now, I knew that because I set it up that way, but we should, if in any collision, the only thing that, well, I shouldn't say this is always true, unless there's some kind of explosion during the collision, the only thing that you could possibly do is either maintain energy or lose energy, unless there's some kind of explosion, or things, a spring that pops out or something like that. All right, so that's all the examples that I had for today.